Thank you very much for inviting me, and my apologies for not being able to be there in person. But yes, like the last speaker, I would like to talk about exploring the outer solar system, and I'm going to take a broader view and try and focus on a variety of different projects that might be possible. So very briefly, I'll talk about the problem. The problem, of course, is the long transit times, and then I'll discuss where we could go and why we might want to go there. And the bulk of the talk is going to be 5 examples of what we could do at specific locations. And the reason for picking these specific locations is partly because they're scientifically interesting, but also because a fair amount of effort has already gone into imagining what you could do with a spacecraft at these locations. And so these have a certain amount of heritage. Now, of course, the spacecraft that were considered were more massive than the kind of spacecraft we're talking about today. But nonetheless, people have thought quite seriously about all of these targets in a way that I will summarize. So the outer solar system has lots of really interesting objects. The Kuiper belt, which is the furthest reaches of the solar system, has many objects, only one or only a pair of which we've actually explored. Everything else is an artist's impression, but we know they're interesting. Eris is as big as Pluto, which turned out to be fascinating. Haumea is very distorted and has moons that suggest it was hit by something hard and partially fragmented. So there's lots of interesting stuff in the outer solar system, in the Kuiper belt. And that's not just true of Kuiper belt objects, it's also true of moons. This is a rogues gallery of moons of the outer solar system. We already heard a little bit about Triton. Titan is an interesting moon because it's the only moon to possess a thick atmosphere for reasons that we don't understand. And one of the big stories of the last 10 years is that many of these moons probably have oceans beneath their surfaces. The ones marked in blue most likely have subsurface oceans. So these are very interesting and diverse objects too. But of course, the problem is that they're a long way away. If you want to get to Neptune, Neptune is at 30 times the distance to the Earth, from the Earth to the Sun. If you want to get to somewhere like Eris, you have to go, more like 90 AU. And so the outer solar system is a long way away. And in fact, as was already alluded to, in the last 50 years of spacecraft flight, only 5 spacecraft has gone beyond Saturn. And so we really haven't done a good job of exploring the outer solar system. And the reason for that, of course, is that the flight times are long. So even New Horizons, which was traveling very fast indeed, took almost a decade to get to Pluto. And that is not only inconvenient, it both adds cost because you have to have people managing the spacecraft, and it also adds risk. For instance, if one of your radio thermal generators fails, then you're going to lose the mission. And so the increased flight time leads to increased risk. The traditional solution to this has been to use a Jupiter gravity assist, but the problem is that the alignment only happens typically once every 12 years. And so there are decades when you simply can't launch to a particular target. And this is just to illustrate the problem. This is from a decadal study. I know it's an eye chart, but all you need to do is to look at the column on the right-hand end. You can see that there are lots of interesting targets out there. You can fly past a moon of Uranus and then go on to a Kuiper belt object, but it's going to take you 20 years to do so. You could fly past Triton and then go and visit Eris or Sedna, which are big, interesting Kuiper belt objects, but then it's going to take you 30 years. And so the flight times with the traditional technology are just prohibitively long. So, as we've heard, these small, fast sailcraft could solve this problem. If you're going at even just 7 AU a year, that gets you to Neptune in 5 years, which is pretty impressive. Now, we do have some experience of fast flybys like that. New Horizons is the type example. It flew past Pluto at 23 kilometers a second, which is fast. But of course, it was a much larger spacecraft than the kind that we're talking about. And it's not huge, it's the size of a grand piano, but still, it was half a ton launch mass. So the topic that I'm really interested in is probing the structure and evolution of these bodies in the outer solar system. And at least for the moons and the Kuiper Belt objects, there are really two fundamental questions. The first is, have they separated into an ice layer and a rocky interior or not? That tells us something about their thermal history as well as their present day structure. And then the second question is whether or not there are subsurface oceans. And the reason that that's important is that if there are oceans, then these places represent potentially habitable environments. We might find life there ultimately. And there are a variety of techniques that we can use to answer these questions, but I'm really going to focus in on four. Obviously, you can use imaging, not only just to look at the surface, but it turns out that the shape of the object can tell you about whether it's separated out into rock and ice or not. Similarly, gravity can also tell you about whether it's differentiated or not. It turns out that a magnetometer is actually a very useful instrument to bring, and that's because if you have a varying background magnetic field, then the ocean will produce an induction signature that is actually easy to detect even on a single flyby. And so if you want to look for oceans, carrying a magnetometer with you is a very powerful technique. And then finally, if you want to know what these objects are actually made of, a good instrument to carry is a mass spectroscopy. You can, for instance, fly through the plumes of Enceladus and measure what their composition is. That tells you about the general makeup of the object. So I'm going to switch now to talking about these 5 specific examples. And the first one is actually one you've already heard about from the previous speaker. And there's a good reason for that. Triton, which is the only big moon of Neptune, is an extremely interesting object. One reason it's interesting is that it didn't start out life like that. It started out as a Kuiper Belt object further out in the solar system that somehow got captured by Neptune early on. Perhaps as a result of that capture process, you can see that the surface is very young. There are almost no craters on Triton, but it's heavily geologically deformed, and it's in fact active at the present day. There are geysers jetting into space. These dark blobs here are the traces of geyser particles that have fallen back to the surface. So it's geologically active, and it's widely suspected to have an ocean beneath the subsurface. So it's very interesting from an interiors point of view. It has a thin atmosphere, and it also has an unusually intense ionosphere. And so for people who are interested in the things above the surface, Triton is also a very attractive target. And so you can do a lot on a single flyby. So Triton was seen as a sufficiently interesting target that it was one of the finalists for the last discovery round. And obviously, this is a big, capable spacecraft, but you can see the kind of instruments that are being brought. You bring a magnetometer, you bring a couple of cameras, you get radio science for free, and you have a plasma spectrometer. And the flyby speed is comparable to New Horizons. So this was a very fast flyby. And on the left, we just have an example of the kind of observations that you take as you do your flyby. Notice that you can also actually get data from Neptune, but the point is that this is very compressed. From 3 million kilometers out to closest approach is only a single day. So you have to take a lot of observations in a rather short period of time. Another option that was explored by the last decadal was the idea of flying past the moon, like Triton, but then keeping going and actually targeting a Kuiper Belt object. You could fly past one of the Uranian moons. The Uranian moons are one of the last sort of terra incognita of the solar system. They were only visited once and were only imaged rather poorly, but they're fascinating objects, partly because they too probably have subsurface oceans. And as we heard, they're likely to be a future flagship mission target. So you could fly past a Uranian moon, or you could fly past Triton, and then you would go on to encounter a Kuiper Belt object. As we saw, Kuiper Belt objects appear very diverse, but we've only ever visited one. And so, again, you've seen this chart before, but now the thing to do is to focus on the kind of worlds that you could visit. For instance, going past Triton and then visiting Eris, or going past Triton and then visiting Sedna would be an extremely interesting combination. But again, with conventional spacecraft, the flight time is in the sort of 3-decade range. Something that's come up relatively recently is that every so often an object from outside the solar system whizzes through. So far we've seen one of these things called Oumuamua, and these would be interesting targets because they might have fundamentally different characteristics to all the bodies in this solar system. For instance, the carbon to silicon or the carbon to oxygen ratio might be completely different. And so it would be very interesting to go and look at one of these things. Similarly, there's a class of comets out there that have never come close to the sun. And so if you could catch one of these long period comets before it's ever encountered the sun, then it will never have been baked. And so you'll be getting a sort of pristine sample that so far we have never managed to do. The problem with both of these targets is that they're moving very fast. Oumuamua was traveling at 87 kilometers a second. And so you have to move fast to catch either of these. Another, I think, rather good option is to think about delivering an atmospheric probe to a giant planet, to Jupiter or Saturn, for instance. The reason that we would want to do that is because we don't know the isotopic composition of these giant planets, certainly not for Saturn or Uranus or Neptune. And we would very much like to, because the isotopes contain clues as to where those planets actually formed in the first place. We don't actually know, and we suspect that the planets may have moved around. And so by making isotopic measurements, we can get a better idea of how the planets in the outer solar system were assembled. And the big advantage of an atmospheric probe is that it's much smaller and lighter than a conventional spacecraft. Even the Decadal Study Uranus probe, which is a pretty sophisticated instrument, it's, you know, a third or a quarter of the mass of a spacecraft like New Horizons, and it doesn't take much power compared to a full spacecraft. So it seems to me like this might be a sweet spot for small, fast sailcraft. And then another interesting idea is that you could actually just crash something into the surface. This has been done a couple of times. It was done as a comet and it was done on the moon. And the idea is that the collision creates a vapor plume that you can then measure with a second spacecraft. And so with a pair of spacecraft, you can actually do some fairly interesting science. And here, high velocity is an advantage. The faster you're traveling, the bigger a vapor plume you produce. One thing that I will mention, because I think it probably won't work, is that it would be very nice to fly through the plumes of Enceladus and measure their composition. The trouble is that if you do this at high speed, then the molecules actually break up as they enter the mass spectrometer. And so what you measure are fragments and not the original molecules that you're interested in. And so at least with existing technology, this was certainly a problem on the Cassini spacecraft. And I think at higher speeds, it will be even more of a problem. So some more tech development would be needed there. Okay, you don't need to take this too seriously, but as we just heard, the Decadal survey came out and posed a series of what are regarded as top-level questions. And the point is that each of these mission concepts does a pretty good job of answering one or more of the fundamental decadal questions. I think the only one that doesn't really do that is the Interplanetary Interceptor, and that's simply because we haven't really had enough time to think yet about what questions you would even ask if you did intercept one of these objects. So the point is that even a fairly limited mission to one of these targets would be answering fundamental questions. One potential architecture of having more than one spacecraft is potentially very powerful, and it's not something we can normally do. For instance, if you're interested in space physics, it really helps to have two platforms, because then you can distinguish between things that are varying in time and things that are varying in space. And similarly, with the impactor and follow-up pair, you need to have multiple spacecraft. If you have spacecraft to spare, then you can also do unusual flyby geometries. For instance, the poles of planets are generally not observable from Earth. And so if you do a polar flyby, then you are accessing an area that can't be got from terrestrial observations. And then because so many of these objects are totally unexplored, even if you have a very limited payload, you're still going to get useful information back. Okay, I'm just going to spend a couple of minutes on the technical challenges. I think these are probably obvious to most of you. The most important one, of course, is mass, that conventional instruments are heavy. A narrow angle camera is 11 kilograms. You know, a magnetometer might be a bit lighter, but still, these are heavy instruments. And so, as we heard in the last talk, clever approaches to miniaturization are very important. Velocity might be a problem. It's going to limit the time of observations that you can make. You may get imaging smear, but I think in terms of imaging, these are not insuperable. I think the one thing that it will stop you doing is gravity science, which makes me sad. But the point is that if you're traveling that fast, you just don't get, your orbit doesn't get perturbed by the mass you're flying past. Power is obviously an issue. RTGs are heavy. If you get beyond Saturn, say, solar power is not very effective. And so this is, I think, probably an unsolved problem at this point. And then similarly, communications is always going to be an issue. If you have a small craft and there's low power, then there's going to be just a slow downlink, and there's not much you can do about that. That will certainly require more onboard autonomy than we're used to thinking about. So let me finish up. I think there's little doubt that small, fast spacecraft could really change the paradigm in the exploration of the outer solar system. And as I've hopefully showed you, there are many places that we could go to that have not been explored that look extremely interesting. And from my analysis, I think thinking seriously about atmospheric probes and thinking about impactors are probably the low-hanging fruit at this point. And again, even if you have a very limited payload, if you're going to an object that's completely unexplored, you're still going to learn lots of interesting new information. But of course, significant technical challenges remain, and so there's a lot of tech development still to be done. So that's my brief summary. Thank you for your attention.